So let's continue then with this point in polygon notebook that now brings us to the topic of spatial queries, investigating spatial relationships using GeoPandas and Shapely. So this section or this notebook, it's a bit kind of, well, conceptual or a bit simple, let's say so. So the examples in here are a bit arbitrary. But then in the next, when we continue with doing spatial joins based on these spatial relationships, then we have a more concrete example. But here the goal is to familiarize ourselves with the basic spatial relationships and how can we investigate those in Shapely and then in GeoPandas later on. So there's quite a lot of code readily written. So I have tried to avoid to spend time on typing things in that we already know how to do. Okay, so point in polygon is a very kind of classical analysis problem in GIS overlay analysis. So is a point inside a polygon, or does a polygon contain a point? And based on this information, we can then, for example, join information from a land cover class to your sample plot, or join in like country level information to cities, or these sorts of examples. And there's two main kind of, well, logics in there that I already mentioned. So the within function that checks if point is within a polygon, and then contains checks from the perspective of the polygon if it contains then the point geometry. And these are now Shapely functions. And again, you can then refer to the Shapely documentation for the details. But basically, the syntax is super simple. We have a point object, then the within function, and then this other is often a polygon object or similar. So let's get some points to play around with. We import from Shapely geometry, import point and polygon. Again, we could just call shapely.geometry.point every time we call this constructor, but it's easier to import them directly and then start using those. So you can run the cell. We have point 1 and point 2 in memory. These are now then, well, of course, they're now abstract Shapely coordinates, but these would then represent points somewhere around Helsinki, Finland, in this VGS84 coordinate reference system. Then we have a polygon. So we already know how to create polygons. We have a list of coordinate tuples given to the polygon constructor. You can create that. And then this one just prints out the definitions. Okay, so then we can check if point 1 is inside the polygon that we have just defined. So first object within poly. Actually failed to, if you're annoyed by these printouts, you can run kernel clear all outputs. I'll actually do that to make this make more sense. Okay. So based on this, we haven't yet even visualized them on a map, but Shapely can tell us that point 1 coordinates are somewhere inside this polygon that we have defined. And then for the other point, P2 within polygon, the second point is outside the polygon. We might then want to verify that visually. And well, this is just a curiosity, but in fact, we can also observe that point 1 is quite close to the center point of the polygon. So it's somewhere in the middle. And then the other way around, we can ask if the polygon contains point. That's true. And then logically, this should be false. So the polygon doesn't contain polygon 2, point 2. So these return a Boolean value. It's either true or false, nothing in between. So either it contains or it doesn't contain. And let's actually check. Yep. So this within, the logic of the within returns true if the object's boundary and interior intersect with the interior of the other. So if the point would be on the kind of boundary line, so the just on the border of the polygon, then it would be false. So intersection can happen if the point is on the border of the polygon, but it's not within the polygon. I think we don't have an example of that. Yeah, and then logically, which one you should use? So you can then imagine that we would have geometries in pandas data frames. So you want to do this for multiple objects. So if you have many points and just one polygon, then you might want to use the within command, and then the other way around. If you have many polygons and just one point, you might want to ask if the polygons contain the point. But in both ways, the results should be the same. Okay, then this intersection that I already mentioned. So indeed, if the boundary or interior of one object intersects with the other object, so it could then be only on the border. And then touching means that they have at least one point in common. And for demonstrating these, we have some lines, some very simple lines. And the syntax goes like this. So if we have line A, does it intersect with line B? Oops. Intersects. So that is true. And then we can ask if they touch. So if they have at least one point in common, if they cross each other. So logically, if they intersect, they would also touch. But let's see. Oops. Touches, I think it is. Yes. Touches is the syntax. And here, if we now really want to visualize them without creating, kind of visualize them in the same picture without using Matplotlib or making them into a GeoPandas geodata frame, we can do a little trick that we multi-line string if in case you imported it. So create one object out of these two lines. So you can see that they actually then continue. The second line continues from the same point where the first line ended, as we can already see from the definition. So this point 1, 1 is the point where they touch, and that's the point where they intersect. But then there's this kind of, well, I don't know if it's an exception, but by definition, if we have two identical objects and we check if they touch, so that's false. But then if we have two identical geometries fully on top of each other, they do intersect. So then depending on the analysis case, you might want to use one or the other. And especially with these then intersect and within, it can then affect the calculation. So I think it's, yeah, this week's exercise, we are analyzing population. I hope it's this week's exercise. Apologies if it's the following, but we will create buffers around train stations and then take population data from a grid data. So we will have a round polygon and then smaller grid cells. So if we take all grid cells that are within the buffer, we will lose data on the edges. But if we take all grid cells that intersect with the buffer, then we will get a slight overestimation. So then it really matters, or matters with the calculations if you sum up, take these kind of spatial statistics based on objects that intersect or are within or that touch. So it's good to understand the different logic behind of these. So then, how can we do all this in GeoPandas? We import GeoPandas. Then we have now these addresses that we geocoded. Or if you weren't able to geocode, the file is available in the instance. Should be able to read it in using the skills from last week. And then in addition, we have now actually the population data that I mentioned also in here. So it's this pks suuralue.kml. It's a bit of an old file format, but nevertheless, let's learn how we can import that as well. So last week we discussed these supported drivers in Fiona. If you run this cell, you can see a list of them, including Esri shapefile or GeoJSON or GeoPackage, should be somewhere. Yes, so this is GeoPackage, but there is no KML file by default because, well, it's somehow technically a bit problematic. But in case now that we have the input file as a KML file, we can enable it like this. So I have the syntax ready there. So we refer to the KML key. So by default is disabled, but like this we can enable it so that then we can afterwards also use that driver for reading data from the KML file format. So now after running that, you should then see it in the dictionary of available drivers. Okay, so then we can read it in, have the file path there ready, not to have to type it in, but let's then import the data. So those are then these kind of statistical grid squares that are polygons, so we can call them polys. For example, then GPD read file file path, and now we need to specify the driver KML. That should work. So for this KML file format and then other file formats, we have this tutorial in last week's materials under lesson 2, vector data in and out, with these small code snippets for different various file formats and how to read and write data from different formats. So if you get data in some other format than, well, Esri shapefile, you can then refer to this page on how to perhaps read it in using GeoPandas. But now we have our KML file in there. Let's check what we have. Again, let's take the head. So you can see that we have, well, there's probably 3 columns: name, description that is empty, and then there's this polygon. Yeah, actually these are not statistical grid squares, but these are kind of districts that we can then actually see these suuralue polygons, as the name already indicated. I'm jumping ahead. So after importing a new spatial layer, it's good to just quickly visualize it. So these are now the greater statistical regions in Helsinki. And you can see that the southernmost regions, they then cover the sea area. So that's why the shape is like this. So there should be 23 polygons in our data. And now for this kind of, we have a very arbitrary example to demonstrate the pointing polygon process using GeoPandas. So we will select one of these districts, the southernmost one. We could pretend that we're doing some analysis for the city of Helsinki in the southernmost district, and we want to make some spatial selection for points that are located in there. So first we want to select the data. A bit of recap from previous lessons. So let's create a new variable, then take the input data. So polis.log. And there we want to make the condition based on the name column. So we want to select the row where name equals to eteläinen. You can copy paste it from there if it's difficult to write. So polis name column equals to eteläinen. So if you don't have the Scandics in your keyboard, just go ahead and copy paste that one. That should work. And as a recap, so here's now the condition. So this syntax in here returns a pandas series with true and false values. And we can see that the condition is true only on one row at index 10. And when we give that series as input for the log function, log checks that which rows are true based on the condition and then returns those. So then we can see that we have only the row 10 stored in this output. And now that we have it, or whenever making selections, it might be a good idea to reset the index to start from 1. Drop true drops the original one. If this is false, then we would get a new column with the original index. In some applications, it might be useful to have it in there, and then in place true replaces the values in this data frame with one row. So now I have this one row of data at index 0, this one polygon. And of course, you can, even if you want to plot it, you can do that. It looks a bit funny. So polis.log, polis column name equals eteläinen gives us the selection. And as a result, we get, is it then this one here as a separate layer and separate geometry. Okay, let's investigate it further. We can now refresh our memory of plotting. Week 5 will be all about plotting, but it's good to plot the spatial data every now and then to know that we are on the right track. So let's create a figure with one subplot. PLT. Just like this, you could then define the size of the figure inside here if you would like. So we have the all the districts in here. Let's plot it to the subplot. So the default color would be blue, but as we are plotting now several layers on top of each other, we want to maybe change the colors. And then we can add this southern plot AX equals AX. And then we can give it another color for it to pop up. So here we have now plotted to the same figure object, same subplot, the first layer, and then the second layer on top of it. And then we have read in this point data that we geocoded. So then data dot plot same figure object or subplot object, and then let's see what happens there. So now we have even the points in the same figure. They're a bit ugly because of the marker is so big, so we can adjust marker size equals 5. Okay, so this is now our kind of input data layers for our point in polygon dataset. We have all the districts, we have a selected district, and then we have some point data. And as you might guess from the shape of the point data, they represent some public transport stations in Helsinki. Okay, so then we are now set up for the point in polygon query in pandas. The next code cell should return true before this was disabled by default. But this, because these kind of spatial queries can be rather slow, but nowadays this speedups mode is enabled by default, so we don't need to worry about that anymore. And we can then continue with the actual point in polygon analysis. So now we can take the data, which is the point data. So I can just remind you of that. We have the geocoded addresses in the data frame called data. And our task would be to figure out that out of all of these points, which ones are within the southern district. Of course, if we would just ask which are within the whole set, we would get a different result. But here we want to figure out which ones are within this particular polygon. So we can then call, using these shapely functions, we can have a geodata frame dot within, then we need to pass the other geometries. So if we call it like this, GeoPandas understands that we are referring to the geometries in our data frame, so this column. But then for the other objects, we need to pass a geodata frame. And how can we then get the geodata frame of our target object? We can do it like this. So if you did reset the index, we can just pass. So this basically returns the polygon definition of our southern district. So then the syntax goes so that for all of the points, true or false is the point within this polygon. So this is kind of this many to one comparison. Oops. Southern. Okay. And then this will return true or false for each row. So comparing each point at a time to this one polygon that represents the southern district. And then we can see that some of them are within, so it's true. Some of them are not within, so it's false. And then we can use this as a kind of mask or a condition for our final result. And for that, to make the syntax more clear, let's store this in a separate variable. So this pip mask is now a pandas series with these true and false values. Many typos today. And then now that we have the information for each row, we can again use this data.lock and then pass this true and false series. So pip mask and lock will go and check which rows have true. Let's return all of those rows, and we have maybe 1, 2, 3, 4, 5, some less than 10 rows that represent the points that are within the polygon. I'll call this pip data so that we can investigate it further. So now I have the selected rows based on this spatial selection in this pip data, geodata frame, I assume. Okay, so I would suggest, I've been talking now for a long time, so let's take a break, but we can start the break or end the break so that then you now try to plot these points with a different color on top of this map. So you could do so that you copy paste this syntax in here. But then instead of these, instead of plotting all the points, try to plot these selected points on the map. And we can then still discuss this after the break before we continue to another example of spatial joins. So let's take a break. Let's take 12 minutes, so returning at 16:40. And we will then wrap up this first set of point in polygon examples. All right. So if you want, feel free to play around with the plot and try to modify this script so that you can then plot this subset of the points on top of this map. No niin. Welcome back from the break. I hope you did some thinking about plotting and the spatial relationships that we are now investigating. So our points within the polygons and how we can put that in place using geopandas and shapely objects. So we now were able to use this within command. So geodata_frame.within then takes all the geometries in this geodata frame and then compares all of those to the shapely object passed in here. So I couldn't do, if I would do like this, let's see what happens. So there might be something funny going on. Maybe I take that example back because I haven't really thought about it, but this is at least clear. I'm passing one shapely polygon to be compared with all of these points. And then for each point I get result, is it within this polygon or not? Then for the final task of plotting, we again created a figure with one subplot, plot the polygons in there. And then we have this output of the selection in the variable pip data. So then I can take that one, pip data.plot to the same subplot object. And then what is the parameter? Just color for the point object. I can define the color gold. To plot it in there just to verify that the logic seems right. We have now visualized the points that are within the polygon. And that's how it goes. If you have some questions at this point, we can still recap some of these things. But the main point of this tutorial was indeed to introduce the main concepts of a point in polygon query and see how we can do that using Shapely and GeoPandas. Once that's done, we can move on with the lesson to spatial join section. So we have now two main themes still now after the break. So this, where we then actually, in addition to subsetting data that we just did in the point in polygon tutorial, often we want to investigate these spatial relationships in order to join data from one table to the other based on spatial location. It's the same procedure you can execute in QGIS or ArcGIS and other desktop software, but then of course with Python we can then repeat the process automatically for a larger number of input layers, for example. All right. So for example, we could join the attributes of a polygon layer into a point layer that intersects or contains the point. And this would be a useful thing if you have some measurements with GPS coordinates and you want to link some land cover data to those or some other data from a surface. Just as one of the examples. So for these spatial joins, we can use this readily available function in GeoPandas called the sJoin. So a bit similar to this join in pandas, but this is then sJoin, which then operates on these spatial conditions. Let's have a quick look of the documentation. So indeed, two geometry objects, basically attributes from two data sets are merged based on their spatial relationship. And this function has two arguments, op and how. So the op is, I guess it stands for the option or the spatial condition. So do we want to investigate if the objects intersect, or if one is within the other, or if one contains the other. So the same conditions that we already saw in the previous tutorial based on Shapely. And then this how parameter. So if we set it as left, so we always have data frame dot sJoin another data frame. So I'm in the mirror to the camera, but the left, if we make a left join, then we take kind of the index or the rows of the first data frame as the starting point. Then we do the join. And then in the output will have all the rows from the first data frame, regardless if they found a match. So let's say the first data frame would be a polygon object, and then we join some point objects. So if some point objects are outside of the polygons, or if some polygon doesn't have a point inside it, it would still be in the output. And then the other way around, if we do a right join, so if we join data frame 1, sJoin data frame 2, so then if we do a right join, then we have all the rows from the second or the right data frame in the output. And then if there wasn't a match, then we lose some records from the first one. And then an inner join contains the matching records and then discards. If the polygon didn't have a point inside, it won't be in the output. So it's good to be aware of these different ways of joining data. And this applies to both spatial and aspatial join operations. Excellent. So we can actually go back to the cloud computing environment. Under lesson 3, there is this notebook number 3 called Spatial Join. I will close that one, and we can continue in here. The first code cell contains a script for accessing our input data, and here we will actually get this population grid data. So a gridded data set that contains population information from the Helsinki region. You can just run it, and I'll briefly explain what's going on. So the similar syntax you can find from last week's in and out vector data in and out tutorial under GeoPandas. But we using GeoPandas and then other packages for making the request from this web feature services by HSY. So the, what is it in English? The regional services in Helsinki. I should know that. What is it in English? Anyway, so they have a web feature service with open geospatial data that we can access. And the web feature service refers to the fact that it's vector data. And then you need to know the URL to the data provider, and then you need to know the name of the data layer. So this is now in Finnish. Basically, it refers to this group of data related to land use and housing. And then we have the population grid from 2018 as the actual data layer. So these are then the parameters for our request from the web feature service. And then we can get the data using these parameters and finally parse this JSON output to geodata frame. So there's many lines of code, but you can use the same syntax if you're fetching some other layers from the same provider or from some other providers. I should maybe later show how you can actually, I often first check from QGIS how the web feature service looks like, what layers there are, and then modify the Python code accordingly, according to which layer I want to fetch using Python. But that should work as such. We can then check what we get out from there. So in the variable called pop, there is a pandas geodata frame with multiple columns. They are again in Finnish, but we will rename them. So there's each row represents a statistical grid square. They have an index, population count, asukas values, well, somebody can translate that to English quickly, and then population count per age group in the separate columns. And we are particularly interested in the population count in each grid square. I'll still check how many rows we have. So there's some 3,000 grid squares in the data. A little bit of recap of the useful pandas skills. So we first want to modify the data that it's easier to handle using the rename function. And we want to target the asukkaita column. You can paste it from here if it's difficult to spell. So the column that has this name, we want to rename it as POP 18. That stands for population 2018. And renaming happened using a dictionary with key value pair in these curly brackets. And if, yep. So we rename it and replace the values of our data frame. In the same cell, I can actually then check. Okay, So after successful renaming, you should see a geometry column, index column, pop 18, and then all these other columns that we won't be needing. So then again, we can subset the columns. We only need pop 18 and then geometry. So we need to pass a list of column names inside these curly brackets of our data frame, not curly, these, well, brackets, to arrive to this situation. So we have a clean geodata frame with only the columns we need. So always when you start analyzing data, especially in Python, good idea to throw away everything you don't need, because we are just working in the memory, Python memory. We are not modifying the original data. So it's no harm to throw out columns that you don't need. If you want to add something later on, you can modify your script and add, let's say, the population count for kids aged from 0 to 9. Why not? Okay. I hope you got this renaming, subsetting columns. If I'm going too fast, then you can check the websites. And somebody was kind enough to translate asumis values, which was this us values. So it's the density or rate of occupancy maybe. So the number of people divided by the land area, basically. Should refresh my geography vocabulary once in a while. So then we will conduct a spatial join. And for that, we will once again import these address points that some of us were able to geocode at the start of the class. If not, the layer is available in the data folder. So we defined file path, read in the file. We've done that many times before. Let's just check what we have. Addresses.head. So we have this original addresses, geocoded addresses, and then they have the point geometry. Next, as we are doing spatial joins, it's good to be aware of the coordinate reference system. Addresses.crs, so we covered coordinate reference systems last week, but let's not forget about them. So we can observe many things, but two key things. First, this layer has a CRS definition, so we didn't lose the PRJ file. And secondly, the coordinates are in this EPSG 4326, so VGS84 coordinate reference system that we can already see from the geometries of this data. Good to know. Then we have this pop CRS from the web feature service, which actually doesn't have a CRS. We could have defined it before when reading in the data, but we can also define it now. So if you are 100% sure of the CRS definition of your layer, then you can just add the definition to the layer. And if we check the values, you can see here that these are definitely not VGS84. It's some kind of local projected coordinate system. And from the documentation of the data, we can find out that that is actually this EPSG 3879 CRS that belongs to these coordinates in this population grid data. So this should go to the metadata page that has that information, I hope. So then we can do that pop.crs equals to coordinate reference system definition. And we have already imported PyPro CRS in here. So then we can call the CRS object, like we learned last week, from EPSG, and then pass the number. And actually, this should be enough. And then to check pop CRS. So now we have the definition. But again, I want to remind that if you do this and you just give some random coordinate reference system number there, it doesn't change the actual coordinate value. So this needs to be match the data. So this is just a definition or a description of what is the CRS, but the actual coordinates are in some specific projection, and defining the projection doesn't change the coordinate values. And I think there's some steps in the exercise. If you if you don't understand this, the difference between defining and reprojecting, you might end up in trouble, because then if the CRS definitions are not correct, then the data won't be spatially overlapping, and we can't do or we can do spatial joins or ask the spatial questions, but then often the result is that nothing matches, everything is in a different place, no overlap. Then, as we're doing overlay analysis, it's important to ask if the CRS are the same. So we can use this Boolean, do a Boolean comparison. And logically, they are not the same. So we can't yet ask any questions about their spatial relationship because the CRS don't match. Luckily, we know also how to reproject coordinates. So in here, well, it's a bit boring. It was already written in there, but we now reproject the addresses to the coordinate reference system of the population grid. And we can do that by calling the name of the geodata frame to CRS, and then on the fly, we can say that, hey, convert this layer to the same projection as this layer. And there's a reason, well, I think it's a good reason why we are converting the CRS or reprojecting the points rather than the population grid, because the population grid is a local dataset from Finland. There's a good reason that we have this particular projection, and there we can measure distances. It's a metric system, and also as the kind of polygon data is more complicated, whereas point data is more simple, there's less risk of introducing some weird stuff in the data if we reproject the points to the same coordinate reference system as the polygons. And then furthermore, if we would start doing calculations on distances, then we definitely want to have them in a projected coordinate system. Okay, so after that lecture, we can again check the CRS definitions. This is very important point, which can then, if you kind of make a mistake here, the rest of the analysis is meaningless if the CRS definitions are wrongly defined. So always pay attention to the CRS if doing a spatial overlay analysis. Addresses.crs, it's a bit slow, print pop.crs, looks good, and then we can still verify pop.crs. So I often have in my scripts, if I'm doing some spatial joins, I often have a little function that checks that do the CRS match. If not, reproject one or the other. If they match, just continue without doing anything. Or if they don't match, give me a warning and then I'll check it manually. So this is a standard thing to check before proceeding. finally, we can then do the spatial join. We have 2 layers in the same projection. Everything should be fine. And we have this geopandas gpd.sjoin function. It takes, so we had this left and right input data frame. So we have addresses is now the left one, pop is right one. We could have them other way around, but using this order, then we have how. How is inner, so we want only the matching records in the output, and then this op is within. So now we ask if point is within polygon. We could have them the other way around and then ask if polygon contains point, and then this should be contains instead of within. So you can try different options, but if you do as I do, you can create a new variable for the output, not to replace any data. Join head. So now that we passed addresses first, so the first columns are from addresses, then pop, we will get then information from that data frame as the last columns. And then we can then see in this, the way we did it here is that each row still represents a point. So the geometries are from the kind of first layer, but then we have the information that within which polygon this point was located. And then we have this index of the grid square and then the population count of that grid square. Let's still check how many rows we got. There's 27. Originally, we had, oops, what was it called? Addresses. 34 addresses. So this is now related to the inner parameter. Now that we said inner, join between addresses and pop, and we get less results than we had given to the join function. That means that some of the points must be outside the polygons. If we would do a left join, I'm improvising, but let's see what happens. Then we would get 34 rows in the output, and then some of the points would then have no data, as you can see in here. So then there's no data about the related grid in the output because there wasn't no spatial, or it wasn't within, it was false, the spatial condition. But I'll turn this back to inner, but maybe this helps you to understand a bit this left, inner, right setting. There we go. Then again, let's check all of this on a map because we have spatial data. Using matplotlib, there's a figure with one subplot with a bit bigger figure size readily defined. Then we can plot the pop. Plot AX equals AX. So let's just plot the grid there as blue. So these are all the populated grid squares in Helsinki 2018. And then on top of that, we can plot the addresses. AX is AX, and then let's put them as red so we can see something, and then you can try different marker sizes, but this should work. So if you see closely, we could even plot a bigger figure, but there's then probably over there, this is, I would say, is it then Kulosaari metro station? There is one over here. What might it be? So there's some of these points that represent these public transport stations that don't fall within any of these populated grid squares. But then for the rest of them, we have now information of the population in the vicinity, so in the grid square within which each point is located. And in this week's exercise, you will get to expand, like make the analysis more meaningful. So we will create buffers around the points. I hope it's this week's exercise or not next week's. Anyway, buffers, and then analyze the gridded data within or intersecting those buffers. Okay, so that was most of it. There's still then if we think of it from the point of view of the points, so if we want to plot the points with the population info that is linked to them, so that was in our variable called join. So we can plot that. Let's see. That only gives us these plots, and if I wanted to the bigger figure, I need to add this AX equals AX. So using pandas, I can kind of create a quick and dirty map which visualizes the values in a specific column with different colors. We will continue discussing data classifications next week and the following week in terms of thematic maps. But let's just see quickly if I define this pop18 in the point layer. Now you can see something happening, but we can adjust it further. So we can define a color map, for example, reds. So the darker the red, the more people were joined from the grid square within which the point is located. And then, well, then there's different parameters if you want to adjust the classification, but indeed we will discuss these better next week. But if you put quantile classification, you can see the difference is a bit better. So logically, these points were located in the city center. So there's quite a lot of people, and then less in the more light colored points. And you can also add a legend to the figure, which then shows these data ranges. So the maximum value of people in the grid square is 1,800 people in some of probably in the city center. Okay, then there's still another code cell. We'll just run it and see what it produces, because we will create these thematic maps next week. But using the same logic, you can of course then visualize the underlying data in the population grid square. So this is now a teaser for the next 2 weeks when we will start plotting data a bit more to visualize the maps. Yeah. Finally, if you run that, you will get, we are saving now the output of the spatial join to file, which has the addresses and then the population information joined from the grid squares to the points. Okay. And the same logic again you could use if you had some measurements in some land cover classes and you had your field coordinate points or whatever else. So good to think about the structure of the output you want, and then create the query and join the data based on that logic. Good. And this is one of the core contents. Spatial join is one of the core contents in this week's exercise. So I'm sure you will get to kind of figure it out yourself also during the next week. Good. Then we still have some time left and one topic to cover. So let's move on to the nearest neighbor analysis, also related to spatial relationships, but then maybe one step more complicated. So you could think of examples, for example, that which bus stop is closest to my home, or which fire station is closest to my home. So in this kind of nearest neighbor analysis, you have maybe one point or target point or multiple, and then another set of points, and then you want to find which one is the nearest. And in this case, we are talking about Euclidean distances, so kind of straight line distances, linnuntieetäisyys, instead of network distances or travel time distances. We will cover network distances in the last lesson. So if you want to do routing analysis, what is the quickest route? But here we are just looking at in the specific coordinate system, what is the nearest point from a set of points to some other point. And this then forms the basis of more complicated nearest neighbor analysis. Now let's then take in the cloud computing environment notebook number 4. And continue. Again, we start with Shapely to introduce the concept, and then we have a bit more complicated case using a pandas data frame and some real world data. We start by creating some points to play around with. You can run that. So we have this kind of origin point and then multiple destination points to start with. And the question is that which one of these destination points is closest or nearest to the origin point. And in Shapely, in order to analyze this problem, we want to create or kind of merge the destination points into one multi-point object. We imported that constructor in here, so we can call it and then put a list of points. So dest1, dest2, dest3 in there. We get a multi-point object, and I will save it to a variable with a logical name. So destinations can print the definition. So it's a multi-point. And indeed, we already saw the geometries, but there they are. So we want kind of Shapely wants one object for the set of points from which we want to find the nearest one then to some origin point. Excellent. So then there's this nearest point function in Shapely, which works like this. So we have points, we call it like this and pass as the first parameter the origin point, and then destinations. I actually would like to, did I have a link in here? If we quickly check Shapely documentation, so nearest point, geometry 1, geometry 2, returns a tuple of the nearest points in the input geometries. The points are returned in the same order as the input geometries. So let's see what this does with our input. So we have one origin point and multiple destinations. Oops, Control Enter that. So then we get 2 outputs. Let's store that into a variable and explore it further. So if we have nearest, oops, caps lock, nearest geoms, so as promised, we got a tuple of the nearest points. So we could have a set of points and another set of points like this, and then Shapely would return the nearest points. Now we have one point and then a set of points, so then it returns these 2 points. I hope this illustration makes some sense. Now let's check the contents further. Well, we already saw it, but if we print it, nearest geoms, it's still, we see that there's 2 Shapely objects. We have a tuple. Which is list-like, so we can access the contents using the indices. So at index 1, we have, well, we had only the one origin point, so it is this one. And then I just copy and paste, and from index 1, we have the point that was nearest to this origin point. So that's the logic. In the output of this nearest points function, we get a tuple which contains the nearest, those points that were nearest in these 2 sets. And it's maybe easier to understand now that we pass one origin and multiple destinations. So this OD matrices or origin destination pairs is typical kind of data structure. For example, if you have some commuting data or any type of accessibility data, even in this travel time matrix, we have the concepts of origins and destinations in there. Then how to do this in GeoPandas? I have to say that the example, well, let's see it first and then I explain. So I have the code cells ready where we import GeoPandas and then read in some input data. You could just run those lines in there. So in this section now, our goal is to find out the closest addresses to the centroid of each district. So we will now recycle some of the data we have already seen during this lesson. We have the geocoded address points, and then we have the suuralue, so the greater districts polygons. So we want to analyze the closest address for each centroid of each district. It's a bit, again, a bit arbitrary, but we can use the data that we already have. Let's check the data that we have. So data frame 1 contains these suuralue district polygons, and then the addresses, data frame 2, contain the geocoded addresses with related attributes. And then before calculating any distances, we should reproject the data into a projected coordinate reference system. Otherwise, you will get a warning, or at least when calculating the centroids. So let's do that. And here, I didn't have time to write it down there, but I recommend we use this EPSG 3067. I'll Google it quickly. So it's a common coordinate reference system used for data from Finland. You might see related to many open data sets. Okay, so how can we do that? df1 to CRS EPSG 3067. And let's replace the values. So data frame 1 equals data frame 1 to CRS EPSG is G3067, and then the same thing for data frame 2. So that's preparation step number 1. And then Secondly, we wanted to analyze the nearest addresses to the centroids, center points of the districts. So we need that information to data frame 1. A bit of recap of the Shapely options in GeoPandas. So we can populate that new column with the centroids of polygons in data frame 1. There we go. So we have a data frame, geodata frame. This is the official geometry column, and then we have an additional column with Shapely objects that contain the centroid. And a curiosity, if you would want to then visualize these centroids, you could just reset the geometry column of the geodata frame using this column. Okay, then comes the complicated bit, but let's first run it and then try to understand what is going on. So here's a function that we will then apply on the row on the data frame. So our goal was to analyze for each point that represents the centroid to find the nearest address. I hope it was that way around. Yes. And that can't be, there's not an easy way to have a one-liner of doing that. We need to think a bit broader how to implement that using pandas. This is still a bit complicated, the function, but it at least does what we want it to do. So let's store that into the memory, apply it, and then I will return and explain it row by row what's happening in here. But most importantly, we will take each row of the data, then give the other information of the other data frame, and then information of the columns based on which we then do this nearest neighbor analysis. Okay, well, maybe I'll walk you through this briefly now. So then for each row, so kind of we can think of it as the origin point, we have a set of destination points, and we want to find out the pair of the closest ones. So then for this other geometries in the other geodata frame, we want to make this multi-point object, and that in GeoPandas we can do using this unary union approach. And then we use this Shapely nearest points function. We pass the point on that row as input, and then compare to the other points. So this contains all the other points. And then we get a tuple that contains the point and then the nearest point. And then we find from the other geodata frame the row where this point is located to get the data, and then finally get some attribute information based on from some specific column, and in this case we will get the information from the geometry column. Okay. So yeah, this is easier to understand if we implement it. So let's check how we can do that piece by piece. So first of all, this unary union, what does it mean? So we want to indeed have one object that contains all the points when we are comparing one point to a set of points in order to find the nearest pair. So if we now have this other data frame, which is the data frame 2, let's check what was in there. So these are the address points. And if we do this unary union. So we get, check the type. So it's a multi-point object as we had previously. So nothing more complicated than that. It takes the geometry column and puts it into one multi-point object. Put it into a variable, which then contains the definitions. So that's one of the steps that happens inside the function. Function in there, of course, we could already pass this one as a parameter in there if we would design the function in another way. So this one happens when we pass the other data frame, then the function takes the geometry column and creates a unary union out of that to have the set of the points to which we want to compare. Okay, so then if we actually apply this function that we have, so we take the first data frame and apply. And when applying a function, there was this, first of all, we want to apply it on each row. So axis 1, as I explained at the start of the lesson. Then we can modify these parameters. So often it's easiest to just kind of paste the function definition, put it in there and start modifying. And when we pass a function using pandas apply, the first argument is just the name of the function. And we can actually delete the row. So passing name of the function to this apply then automatically gives one row of the data as input parameter for this function when it's applied. The other geodata frame in our case is data frame number 2. So we can define it there. And then we can keep, actually in this case, we keep the value column. So the values, which values we want from this other data frame in the output, we can keep it as default. But then for this point column in our districts data frame, we want to actually pass the centroids because we wanted to analyze the nearest address to the centroid of each polygon. So let's see how complicated this gets. I have some syntax error because I pasted that one in there. And then I get another error, probably some syntax centroids. I think it's then just centroid. Okay, so now if I apply it there, apply the function, give the function parameters inside the apply command, apply the function on each row. So then I get a pandas series that contains the values of the nearest point in the other data frame based on this value column. Okay, I copy that, paste it here, and only thing I change is the value column. So I actually don't want the geometries, I want the ID. So I want to know the ID of the address for each centroid. So then it takes the set of points from the other one, makes the nearest neighbor analysis using the shapely function, and then for that geometry returns the value ID column based on the function definition. Then data frame dot head. Data frame. Let's see. So I missed one step. So this doesn't store the output anywhere. If I want, for example, now this is kind of a complicated spatial join or nearest neighbor join. So I can create a new column in our district data frame, for example, called nearest station equals to applying this function on each row. And then I can take data frame 1 head. So then I have this district, its centroid, and information about the nearest station to each centroid. Okay, I hope my explanations made sense. If not, please ask. There was some error previously, which was solved. So yeah, we will discuss these. There was some errors when plotting these classified maps earlier. If you don't have the map classify module installed, so you will need it next week. That's a good question. And for this nearest neighbor analysis, I admit that this is a bit complicated example and a bit difficult to explain like this, but there is the final task in this week's exercise is about you analyzing which shopping center is nearest to your home location or whatever other location. So there you should use this nearest point function and a bit more simple implementation of nearest point in the context of geodata frames. Excellent. So that's it for today's lesson. You can see that there's more materials on the websites. I'll briefly explain what they are about, and you can then study these on your own time. So as mentioned, doing spatial queries can be computationally intensive, and especially if you have large data sets, they might take ridiculously long time to execute. And of course, we want to do things rather efficiently when programming. And I think the concept of spatial index, even if you have studied and used GIS software for a long time, it might be a bit foreign. So often, if even like using ArcMap, the software asks like, should we construct the spatial index? This will take a little while, and then you just want to get rid of the info box. But what does it actually mean when creating a spatial index? I think this is a rather good figure to illustrate it. So the point is to speed up queries. And when creating the spatial index, conceptually, it goes like this, that if we now here you have some of these polygons in here. So then the spatial index divides the space into these kind of index regions. Is it on the south side or the north side, east side, west side? And depending on the complexity of your data, there will be then different levels. And then when you do a query or an overlay analysis, you will then first kind of get rid of most of the data using these, well, it can be a bounding box or something else, and then only using those data, for example, compare each possible combination, which will then make the computational time significantly shorter. So that's my short explanation of the spatial index. And you can then read more on this page. It's an excellent tutorial on it. And then there's some kind of nice case. So this is materials Henrik added last year. If you want to go through the actual code, you can do that. So for example, here, we first would zoom in the overlay analysis to this index region, and then based on that, do the final point in polygon analysis. Okay, but there's so much code and details that I won't even try to explain it totally. And then there's some kind of justification of what is then faster and what is shorter. And then in terms of this nearest neighbor analysis, if the previous example was a bit complicated, don't worry, there's even more longer code to come. but that especially can be very slow if not done efficiently. So then this tutorial explains a bit more efficient way of doing nearest neighbor analysis with larger data sets. So feel free to also then study this one on your own. You won't need it in the exercise, but you can then, of course, for example, think if your idea for the final assignment would contain nearest neighbor analysis, it would be an excellent case to, for example, take this tutorial and build on that